Good morning, distinguished guests, ladies and gentlemen. Warm welcome to everyone joining us today, both in person and online. My name is Srisangyingcharoen, IF Director. I'm going to be the host for this morning session, opening ceremony. Um, Today marks an exciting milestone as we gather for 2026 International School on High-Energy Physics and Astrophysics, or SHEAP in short, bringing together experts, researchers, and participants to share the insights and force collaboration on modified gravity field. Well, actually, this is the third SHEAP school already. And what makes this year a bit special is that this is our very first time to host an international school. And of course, we have got a fantastic lineup ahead, including lecture and variety of activities. Stay tuned for that. Right. To officially mark a commencement of our event, I would like to invite Professor Dr. Konkanok Inkaninan, Vice President for Research and Innovation, Nalesuan University, to the podium to deliver opening address.
Distinguished guests, lecturers, researchers, and participants. It is my great pleasure to welcome you all to the 2026 International School on High Energy and Astrophysics, or SHEAP, at Nontapat University. It is an honor to have all of you here today, both from Thailand and from different parts of the world. This school provides an excellent opportunity for researchers, students, and experts to come together, exchange ideas, and learn from one another in the field of high energy and astrophysics. I am particularly pleased to see that SHEAP has now reached its 8th edition. This is a wonderful achievement and reflects the continued effort to build an international community for scientific learning and collaborations. This year, the school focuses on topics related to modified gravity, which is an exciting and important area of research. I hope that throughout this school, all participants will have the opportunity not only to gain new knowledge from lectures and discussions and homeworks, but also share their own perspective and develop new ideas. More importantly, I hope that this event will create opportunities for new collaborations and lasting connection among researchers and students. Scientific progress is not achieved by working alone, but through the exchange of ideas and the collaboration of people with different experience and perspective. On this occasion, I would like to express my sincere appreciation to the Institute of Fundamental Studies, or IF, the organizing committee, and all supporting organizations and partners, including Synchrotron Light Research Institute, the National Astronomical Research Institute of Thailand, or NARIT, and the Program Management Unit for Human Resources and Institutional Development, Research and Innovation, or PMUB, as well as everyone who has contributed to making this event possible. Finally, I would like to wish all participants an enjoyable, productive, and inspiring time at Nontapat University. I hope that you will make the most of this opportunity to learn, exchange ideas, and build new collaboration. This is my great pleasure to officially declare the 2026 International School on High Energy and Astrophysics open. Thank you, and I wish all of you a very success SHEAP 2026. Thank you very much.
So I would like to thank Professor Dr. Konkanok Inkaninan for those inspiring opening remarks and for setting such an encouraging tone for our school. Next, I would like to invite everyone to take a group photo in front of the room, please. Yeah, and then we going to start the first session later after the group photo. เชิญอาจารย์ ด้วยครับตรงนี้ยังเหลือเติมหน่อยทางหน้านี่2คนเติมไม่หน่อยครับเดี๋ยวเรากลับไปนั่งที่เดิมครับอันนี้ให้มันเต็มแผ่นนี้เลยครับ Just make it for food. You can move anywhere you want. Okay. Thumb up, please. Okay, thank you very much. ขอบคุณครับ
สวัสดีฮัลโหลฮัลโหล
Okay, so it's about time to have the first lecture. And the first lecture is in the topic of a review of general relativity by Dr. Nontapat Wanwieng from National Astronomical Research Institute of Thailand or NARIT. If we are ready, I would give the stage to Dr. Nontapat.
Okay, thank you. Good morning, everyone. First of all, let me introduce myself again. My name is Nontapat Wanwieng. I'm from NARIT, the National Astronomical Research Institute of Thailand. My research mainly related to gravitational wave physics, in particularly interaction between gravitational wave and quantum systems. Today, I give a lecture on a brief review of general relativity. Since this course is on modified gravity, so my main purpose is not to cover every technical details in the subject. Instead, I will review the fundamental concepts of the general relativity, why Newtonian gravity had to be repressed, why Einstein led to geometrical description of gravitation, and how this idea come together in the Einstein fields equation. I understand that most of you are graduate students, right? So I assume that many of you have already taken an introductory course in general relativity before and familiar with mathematics used in the subject, such as differential geometry in curved manifold or tensor analysis. However, even if you have not learned general relativity before, you can treat this lecture as a broad introduction to the subject. Okay. I will divide my lecture into two parts. In the first part, I will use slides to review the main conceptual steps that led from Newton's theory of gravity to the Einstein theory of general relativity. We will start with the simple question, why Newton's theory not enough, and the need for a new description of gravity. We will look at the problem with the Newton theory and the interpretation of gravity as a space-time geometry. Okay, we then discussed Einstein equivalence principle, which lie at heart and soul of general relativity, together with the notion of inertial reference frames. From there, we then introduced the space-time metric, the notion of geodesic and curvature of space-time, and before finally arriving at the Einstein fields equation. In the second part, we will change the atmosphere a little by moving to the blackboard. Blackboard on my iPad. Okay. There, we will derive Einstein equation from the variational approach based on the principle of least action. This is a systematic and elegant way widely used in modern physics. Okay. Ultimately, this subject falls naturally into two basic questions: how gravity affects the motion of matter and how matter generates gravity. Okay. Okay, let's begin with the Newtonian pictures. In Newtonian physics, space and time are separate and absolute. Space is a fixed three-dimensional Euclidean arena, while times flow uniformly and universally in the same way for every observer. Gravity is described by scalar fields in terms of the Newtonian gravitational potential defined over the three-dimensional space and evolving with respect to universal times. Newton's theory answers the first question, that how gravity affects the matter, the motion of matter, to the equation of motion, which provide the expression for the acceleration. It tells that the gradient of the gravitational potential determines the acceleration of the particles. Okay, for the second question, how matter generate gravity, Newton answered this question to the field's equation written in Poisson equation. This equation tells that the mass density is a source of the gravitational potential. So the theory is the structure of the theory is very simple. Gravitational potential determines the motion of particles, and mass density generate the gravitational fields. However, the structure of space and time remain fixed and unaffected because in Newtonian theory, gravity is not the property of space-time themselves. Okay. Newton theory works extremely well within its domain of validity. That is, in weak gravitational fields and slow velocity situation. It successfully described a wide range of physical phenomena from falling objects on Earth to motion of the planet within the solar system. However, at the fundamental levels, Newton theory incompatible with special relativity in several ways. Newton gravity assumed that gravitational influences propagate instantaneously. If the source moved, the gravitational fields everywhere else changed immediately. This is where the conflict with the special relativity appears. In Newtonian gravity, space and time are treated as absolute, while in special relativity, space and time combine into a single entity called space-time. Measurements of the distance, time intervals, or even whether two events occur simultaneously depends on observer frame. That is the observer state of motion. Therefore, if a gravitational influences were instantaneous in one reference frame, observer in other frame would not, in general, agree that the change occurred simultaneously everywhere. More fundamentally, spatial relativity not allow physical information or interaction to propagate faster than the speed of light. So it is clear that the Newtonian theory of gravity and spatial relativity based on fundamentally different concept of space, time, and causality. There is another problem concerning with the source of gravity. In Newtonian gravity, as we know, the source is simply the mass density. But in spatial relativity, according to Einstein's famous equation, E equal to mc squared, this tells us that mass is equivalent with the energy. So if the mass density can act as a source of gravity, the energy density should contribute to gravitational field as well. In fact, in a relativistic theory, we know that not energy density can produce gravity, but also momentum, pressure, and stress, right? So, therefore, a relativistic theory of gravity requires a new description of both the source of gravity and the gravitational field itself. At this point, many different relativistic theory might seem possible. The clue that lead us toward Einstein field equation, the Einstein field theory, is from the remarkable property of gravity, that is the universality of free fall. Okay. To see why free fall is so important, let us compare gravity with other interactions. In electromagnetism, for example, the motion of a charged particle depends on its charge to mass ratio. So two particles with different charge to mass ratio can therefore follow completely different trajectories in the same electromagnetic fields. For gravity, we can distinguish between two notions of mass. The inertial mass, which tells the resistance to acceleration, and the gravitational mass, which measures how strongly the object coupled to gravitational fields. Experiments show to extremely high precision that these two masses are equivalent. This is known as the weak equivalence principle. So for an object moving under gravitational fields alone, the two masses cancel out in the equation of motion, and therefore the acceleration is determined entirely by the gravitational fields, not by the properties of the object itself. Consequently, freely falling test bodies with the same initial position and velocity follow the same trajectory. This is known as the weak equivalence principle in other form. It suggests something remarkable. In free fall, the trajectory does not depend on the composition or internal structure of the object. It depends on the initial position and velocity only. Okay. This is our first clue that gravity may not act as the ordinary force. Instead, it may be the property of space-time itself. Okay. Einstein sharpened this point into the Einstein equivalence principle. In its original form, this principle states that within a sufficiently small region of space-time, the physical effects of gravitational fields is exactly the same as the effects of uniform acceleration. So the modern Einstein equivalence principle goes further. It states that in a sufficiently small region of space-time, or more specifically in local inertial frames, all local non-gravitational law of physics are reduced to those of the spatial relativity. Equivalently, no local non-gravitational experiment can be detect the presence of gravity. The word local is essential. It emphasized that the entire experiment must be performed within a region small enough that the variation of the gravitational fields and hence the tidal effects can be neglected. Freely falling observers can therefore remove gravity locally, but not over extended region. The equivalence principle, therefore, tells us how spatial relativity survives in the presence of gravity. It remains valid locally within local inertial frames. This leads us to local form of the principle of relativity. Once we restrict attention to local inertial frames, the principle of relativity must also be expressed locally. So it states that all local non-gravitational law of physics are the same in every local inertial frame, everywhere and everywhere in the universe. Here by local law, we mean classical or quantum laws that can be expressed entirely in terms of quantities measured within local inertial frames. The qualification non-gravitational is equally important. We may test particle physics, electromagnetism, atomic spectra, or any other non-gravitational process. However, an experiment designed to detect the tidal effects of gravity require measurements over an extended region, and therefore lies outside the scope of the principle. There is a useful operational ways to express this principle. Imagine two observers in the different local freely falling frames at different places and times, receiving identical instructions for the same local experiment. If the experiments are prepared under the same condition, they must obtain the same physical results within experimental accuracy. The description may differ because the observers may be moving relative to one another. But the underlying laws of physics govern the experiments must have the same form. The principle is asserted to hold everywhere and everywhere in the universe. The local law of physics must have the same form in our universe as they have on Earth today and at the center of the sun or even inside black holes, provided that we consider the sufficiently small region, sufficient small regular region of space-time. We can now translate the physical statement into geometry. If spatial relativity is valid in local inertial frame, then space-time must look locally like Minkowski space-time. However, globally, those local Minkowski regions need not fit together to form a single flat space-time. The failure of these local regions to fit together globally as a single flat spacetime is what we describe as the spacetime curvatures. Mathematically, spacetime is represented by four-dimensional differentiable manifold equipped with Lorentzian metric. The geometry of space-time is encoded in the metric tensors and expressed through the line elements, the expression for ds square. Physically, the metric tells us how space-time intervals are measured. It determines the proper times, spatial distances, light cone, and causal relationships. It also governs the motion of freely falling matters and light, as we know, the geodesic trajectories, as well as the phenomena such as the gravitational redshift and tidal effects. The important conceptual point is that the metric is not merely a fixed background on which physical takes place. It is itself dynamical physical fields. In Newtonian gravity, gravitational field is described in terms of the scalar potential, the Newtonian potential. In general relativity, the corresponding role is played by the space-time metric. Therefore, when we say that gravity is geometry, we mean that the gravitational field is encoded directly in the geometry of space-time, as described by the metric tensors. Okay. Different local observer may use different coordinate system. The laws of physics must therefore be expressible in form that does not depend on any particular choice of the coordinates. This is the principle of general covariance. The law of physics should be expressible as tensor equation. Why tensors? Because tensors have well-defined transformation law. If both sides of an equation are tensors of the same type, they transform in the same way under the change of the coordinates. The components may change, but the form and physical content of the equation remain unchanged. This gives us a practical way to carry a law from spatial relativity to curved space-time. First, write the flat space law in tensor form, and then apply the minimal prescription. We replace the Minkowski metric with the general curved space-time metric, and ordinary differential, ordinary or partial derivative with the covariant derivatives, right? Okay, the resulting equation can then be applied consistently in arbitrary coordinates in curved space-time. So the key message is simple. Tensorial form make the coordinate independence of the physical law explicit, while minimal coupling promote that laws from flat space-time to curved space-time. Informally, a geodesic is the straightest possible path allowed by the geometry of space-time. In flat Minkowski space, a free particles move in a straight line with constant forward velocity. This simply say that the forward velocity does not change along the particle's trajectory. In other words, its forward acceleration vanished. Using the chain rule, we can re-express the derivative of the four vectors in terms of the partial derivative act on the forward velocity. This expression means that we differentiate the forward velocity in the direction of the particle's motion. However, this equation is valid only in Cartesian inertial coordinates. The partial derivative of the vectors is not a tensor in curved space-time. So the equation is not yet generally covariant. We now apply the minimal coupling prescription from the previous lectures, from the previous slide, by replacing the partial derivative by the covariant derivative. We then obtain the covariant equation describing the free-fall motion or geodesics in space-time. If we expand the covariant derivative, we obtain the geodesic equation in coordinate representation form. There is also another equivalent way to define a geodesics. For a massive particle, a freely falling time-like geodesics locally maximize the proper time. And I will leave the derivation of the geodesic equation from this variational principle as an exercise this evening. Okay, and individual free falling particles follow geodesic and feels no gravity locally. However, to detect gravity or precisely the curvature of space-time, we must compare to nearby free-falling particles. Let us first consider the Newtonian description. Here, we have two particles separated by a small displacement. Their relative acceleration is determined by how the gravitational field changed from one point to another point. So relative acceleration is controlled not by the gravitational acceleration itself, but by the spatial gradient of the gravitational potential. If the gravitational fields were perfectly uniform, both particles would accelerate in the same ways, and their separation would not change. It is the variation of the gravitational field from place to place that produce the tidal effects of gravity. General relativity, the corresponding results is described by the geodesic deviation equation shown here. The forward velocity described in the motion of the particle along their geodesics, while the separation vectors describe the displacement between the two geodesics. The equation tells that their relative acceleration is deformed by the Riemann curvature tensors. In particular, the geodesic deviation equation takes a form very similar to the Newtonian tidal equations. By comparing the two expressions, we see that the spatial gradient of the Newtonian gravitational fields corresponds to particular components of the Riemann tensors. So the Riemann tensor is therefore the relativistic generalization of the Newton tidal fields. It tells us that how the gravitational fields vary across the space-time and determines the relative acceleration of the nearby free-falling particles. We can remove the apparent of gravitational field at one point by choosing a free-falling frame. But we cannot remove the tidal relative acceleration. This is why the Riemann tensors provides a physical and measurable description of the space-time curvatures. A single geodesic describes free fall by comparing nearby geodesics reveal the curvature of space-time. We now know the geometry controlled the motion. And next, we ask how matter determines the geometry of space-time. Okay. In a relativistic theory, matter is described by the energy momentum tensors. This tensor contain the energy density, momentum density, pressure, and stress. It also obey the local conservation law shown here. Is covariant, divergence, vanished. Therefore, the geometric side of the field equation must also be symmetric, second-length tensors with vanishing covariant divergence. The full Riemann tensors contains all information about the space-time curvature, but it has our indices. But it has 4 indices. By contracting its indices, we obtain the Ricci tensors, which has 2 indices, and the Ricci scalar, which has no indices. Einstein tensor can be defined from the Ricci tensor and Ricci scalar. Because of the contracted Bianchi identity, we know that the covariant divergence of the Einstein tensors automatically vanish, as shown in the equation here. This is exactly the conservation property required for the consistent coupling between space-time geometry and the energy momentum tensors. Under the standard assumption of the 4-dimensional metric theory, with second derivative, this indices is asserted unique apart from the addition of a cosmological constant term. Here we have the Einstein field equation, which lie at the heart of the general relativity. The left-hand side describes the geometry of space-time, its curvature together with the contribution from the cosmological constant. On the right side, we have matter and energy represented by the energy momentum tensors. This includes not only mass and energy, but also momentum, pressure, and stress. The Einstein field equation the Einstein equation are non-linear differential equations for the space-time metric. Once the matter distribution and suitable initial boundary conditions are specified, the equation determine the geometry of space-time. That geometry then determines the geodesic followed by the free-falling matters and light. Okay. We can now return to the two questions raised on the Newton's gravity slide. The first, how does matter generate gravity? The answer is through the Einstein field equation. Matter and energy determine the curvature of space-time. In second question, how does gravity affect matter? The answer is through the geodesic equation. The free-falling matters and light follow the trajectory determined by the resulting space-time geometry. This relationship is often summarized by Wheeler's famous phrase, matter tells space-time how to curve, and space-time tells matter how to move. Okay. General relativity is not only conceptually elegant, it's also an extremely successful physical theory. Among its classical tests are the anomalous perihelion advance of Mercury, gravitational redshift, the light bending, the gravitational lensing, and the Shapiro time delay. On astrophysical scale, it describes relativistic stars, black holes, compact object mergers, and accretion around compact object. It also predicts gravitational radiation. This was first confirmed indirectly through the orbital decays of the binary pulsars, and gravitational waves have now been detected directly from compact binary mergers. Finally, general relativity provides the basics framework for modern cosmology. So any proposed modification of the gravitational field equation must reproduce these successes in every regime where general relativity has already been tested. Okay. The modern viewpoint is that general relativity can be treated as a low-energy effective field theory, the leading description of gravity at low energy and low curvatures. This explains how GR can be extremely successful within its domain of validity without being fundamental at all scale. The left column points towards quantum gravity. Near Planck scale, quantum effects of space-time should become unavoidable. Perturbative quantization of GR is non-renormalizable, and black hole and cosmological singularities mark the limit of the classical description of GR. At the right column shows the cosmological puzzles that may motivate modified gravity theories. Is dark matter new matter or a change in the gravitational law of the gravity? Cosmic acceleration leads us to dark energy and the cosmological constant problem. There are also possible tensions among cosmological measurements. However, none of these puzzles by itself prove that GR is wrong. The missing ingredient could lie in matter, gravity, and initial condition, or the interpretation of the data. So, The two directions are distinct. Quantum gravity seeks a more fundamental high-energy theory, while modified gravity explore change to the gravitational dynamics in other regimes. The action principle, okay, we then remove in the part 2. In part 2, I will use slide. Okay, we now move in the blackboard. In the rest part, we will derive Einstein field equation from the variational principle. Okay. Okay. In general relativity ได้ยินไหม In general relativity, the dynamical fields is a metric tensors. ไม่ค่อยถนัด โอเคไหม โอเคเนาะครับ to determine the gravitational field equation, we start with the action. The action. Which is a functional of metric tensor here. Okay, the action for the gravitational system consists of two parts, the gravitational action and the matter action. Okay, the gravitational action, what is the gravitational action? The gravitational action is provided by the Hilbert action. Here, R is the Ricci scalar. Okay. For the matter action, it can be written in the general form in terms of integral of the Lagrangian density. Which is a function of matter fields. The first derivative and also the background metric. What next? I will put the coupling constant in front of the Hilbert action, which by convention written as 1/2 kappa, where kappa is just a constant to be determined later when we look for the Newtonian limit. What next? Once we have a form of the action functional, the next step is to variation of the dynamical fields. If we vary metric tensors from G alpha beta to a little change, as a result, the action will change from S to S plus delta S. And the delta S in general can be written as the functional derivative with respect to the field variable, which here is the metric. To first order. And then, according to the principle of least action or the stationary action, it's required that delta S must be 0. So it's implied that the functional derivative must be 0 for all. Oh, sorry. So if we write the action as a gravitational action plus the matter action, we will give the equation. Right? Or and this is the equation of motion of gravitational fields, which will be Einstein field equation. Our task is to determine the expression for the functional derivative. Okay. We start with the Hilbert action. Again. The variation of this action give the variation. Right? Expand the product of three terms. We get right. Okay. We need a formula for the variation of square root minus g. Which now I can tell you that is equal to the minus 2 for the derivation, I left to the exercise. You have to carry out this evening. Now substitute substitute this formula to above line. We then give now we arrive this expression. The first term will give the left-hand side of the Einstein field equation, and the second term is actually go to the boundary term. And finally, we can neglect this term, neglect the boundary term. For the first term, okay, we now neglect the boundary term for the moment. So it's left the first term. By compare with the general form of the variation of action, the integrand is the functional derivative of the action. This gives the functional derivative with respect to inverse metric. That is we will put this result to the gravitational fields equation written in functional derivative form above. We write again. Minus 2 kappa. Therefore, the left-hand side become The expression in the parenthesis is actually the Einstein tensor. So now we have the Fields equation. Like this. In the right side, it is the definition of the energy momentum tensors. Defined this way. If the matter action written in terms of Lagrange density, oh, sorry. The functional derivatives of the matter action. So equal to square root minus g Lm. หมดแล้วโอเคจบพอดี Okay, now we have Einstein field equation. Kappa is the couple constant. In Newtonian limit, we will find that it's equal to 8 pi g over c squared, c to the fourth. Okay, that's all of these hours. The details can be covered in tutorial session evening. Let's take a break. Thank you.
Okay, so it's 15-minute break. So you can get the bed in front of the room, and then the next session will start in 15 minutes. เห็นน้อยก็มีPongwitกับเก็บเขาเก่งลูกแต่เจ้าเดี๋ยวเก็บเอาแล้วบอกพูดพอมาทำแบบไฟรถก้นจัดI think we need to talk with how you are studying.อะไรนะครับที่กับเลเซอร์จริงๆเนี่ยไอ้ครับไอ้ชาเป็นอินดิโก้ที่น่าจะบอกว่าอินดิโก้มาเป็นอินดิโก้
ในเรื่องผักตำนี้ก็จริงๆนะโดนไปซิวแต่อยากกินแล้วอ่ะ
Okay, before we start, I'm gonna announce something related to the website Indigo here. You can enter the you can access through the website and looking for this timetable or the schedule here. And you can download the lecture notes and the tutorial sheet here on this web page. Okay, just for your information. And for this 1 hour, we are going to have the lecture that review the essence of the field theory. Okay, in 1 hour, and let's see what I can do. Okay, okay, let's get started. Okay, we're going to the. I'm going to. Okay, let's start by looking at how to move from classical mechanics to fields. So in classical mechanics, the dynamical variable is usually obtained by the generalized coordinate, which is presented by Q that depend on the time variable T here. And the dynamics of the particle is described by the action, which is the functional of this trajectory Q here, and which is equal to the time integral of the Lagrangian, which is depending on the phase space. The Lagrangian depending on the Q and the Q dot here. By moving the point particle into field, we generalize the dynamical variable from trajectory to field. And the field here, what I mean by field here is some function that depending on the every point in space-time here. X mu here is basically the point in space-time, which include time and the space. Okay, and by using this as the dynamical variable, we can do the analog. We can do the analogy of the action. I mean, moving from the action of the point particle into field here, we move from the Lagrangian into the Lagrangian density, which depending on the field itself and the derivative of the field. And by the derivative of the field is not is not the time derivative alone. It is the spatial derivative as well, because in the field theory we try to we try to incorporate time and space on the same level. Okay. So, and by the field here that I presented earlier, as the dynamical variable, it vary theory by theory. For example, if you are consider the Klein-Gordon theory, you are working with the scalar field, and this is the example of the Lagrangian of the Klein-Gordon theory. Okay, the Klein-Gordon field or the scalar field, it can be a real scalar field or the complex scalar field. I mean, like for the complex scalar field, the field that well known is the Higgs field, and probably the real scalar field would be electronic field or the dilaton field if you are going to work in like cosmology. And then if you move into the direct theory, you have like the spinor field, and this is the Lagrangian of the spinor field, which is basically the first derivative form, in the first derivative form. And then you have Maxwell field, which contain the vector field, and the Yang-Mills theory, which contain similarly like the vector field with let's say with some additional color charge. And then if you consider, if you are working in the GR, you need to dealing with the rank 2 tensor field with the metric field, and the Lagrangian is, as you can see in the last lecture, it is basically the Lichy scalar. So let's see how to derive the equation. How can you derive the equation of motion from the action? The way we can do is we use the principle of least action, or one can say the principle of stationary action, such that you take the variation of the dynamical variable. In this case, you take the variation of the field. I mean, you change the field slightly and see what the action changes. And the principle of least action say that the trajectory, the classical trajectory, is equivalent to the point of least action. Meaning that if you take the changes in field, you expect that the action would not change. I mean, it would leave the action invariant. Okay, if you do a changes in field here, the action would change by this form here, because the Lagrangian is dependent on field. So you take a partial derivative of the Lagrangian by the field itself, and then the variation of the field plus the partial derivative of the derivative of the field, and this is the chain of the derivative of the field, and then you apply this condition here and do the integral by part. Then you end up with this equation 5 here. The first term is the bulk term. Whatever it is something times with the variation of the field, which is arbitrary. Okay, and then you have the boundary term. So we usually ignore it because I mean, you can ignore it if your space-time have no boundary, or you can ignore it if you apply certain boundary conditions such that it vanish at the boundary. So if you neglect the boundary term, what you have left is the first term here, and if you impose that the delta S here is 0, it means that whatever in the bracket here needs to be 0 as well. So that is how we obtain the Euler-Lagrange equation, or the equation of motion of the field theory. And for example, this is like the most basic example here of the Klein-Gordon field. You take the Lagrangian in this form, and then you see what is the Euler-Lagrange equation here, and you put everything here and do the calculation. You get the last equation here as your equation of motion. It is the double derivative of the scalar field. Okay, let's do another example on the Maxwell field. On the Maxwell field, the Lagrangian is here, -1/4 f mu nu f mu nu. The f is the stress. The f is the field strength tensor. Here define the field strength tensor is the anti-symmetric tensor here defined in here in the box here. And the field A is a vector field, which is basically the gauge potential and gauge vector in combination of gauge potential and gauge vector, if you familiar in EM here. And because it is the gauge potential and gauge vector, some partial derivative of it will turn it into the electric field and the magnetic field, like the curl A is B or something, EM. But okay, so if we trying to find the equation of motion here, you may put this into like the Euler-Lagrange equation. But what I do here, if I'm going to do the the variation of the field. So I do the variation of this field strength here, and then I do the variation of the Lagrangian, or what I get here is the last term here. I mean, you can do it. It's not hard to do. And then I use some algebra. I use some properties such that the anti-symmetric property, and then we write the delta L as this term here, and then do some integration by part here. I do the integration by part such that I'm going to make this as the boundary term. The first term here is the boundary term because it's the total derivative. And the second term is something that time with the variation of the field of the gauge field A, because the variation is arbitrary here. So that means that everything inside the bracket here need to be zero, which is the equation of motion. So basically, this is the Maxwell equation. And to be exact, it is half of it. It's half of the Maxwell equation. I don't know which half, but okay, it's half of it. But another half of the Maxwell equation can be found from the identity. This is like the Bianchi identity of the field strength tensor. You can prove that this is the identity because of the definition of the field strength itself as the anti-symmetric. Okay. The next is probably the most important concept in the field theory, which is the symmetry. The symmetry is important such that it would shape your theory. It tells you that what allow and what not allow in your theory. If you said that the theory would be invariant under some symmetry, you can say that this term is around, this term is not around, things like that. But what is the symmetry in general? The symmetry is basically the transformation that if you change something in the theory, it would not it would leave your physics invariant. It will leave your physics invariant. Mathematically, what leave your physics invariant? Because the physics is described, or the dynamic of the system is described by the action. That means that you expect that if this kind of transformation give your physics invariant, it means that you expect that your delta S would be zero, or the action would be invariant. Okay, but in general, it does. If the action is invariant, it doesn't mean that the change in Lagrangian would be zero. It mean, I mean, that is too strong. That is too strong. By saying that the change in Lagrangian is zero, but in general, in more general sense, you can set the change in Lagrangian is equal to the total derivative of something, because when you taking as the total derivative here, you send the change of the action as some turn into the boundary term, which can be valued upon suitable boundary conditions. Okay. Okay, let's talk about the symmetry. Basically, we can categorize the transformation by into two classes. The first one is the space-time transformation, which is the transformation of the coordinate, right? So you would familiar with the space-time transformation. For example, here is a Poincare transformation, which involve the Lorentz transformation and the translation. And by the Lorentz transformation is satisfy this and this condition. Okay. So the question is, by doing the coordinate transformation, for specifically, this is the Poincare transformation. How do fields transform according to that coordinate transformation? Okay. So the answer is that what I show you in the slide here, each field transform differently, but it's transformed tensorally. For example, the scalar field transform trivially, such that because the scalar field have no index, right? Have no index, so it's transformed trivially, such that the new field at the new coordinate is basically the untransformed field of the untransformed coordinate. Okay, but if you are dealing with the vector field here, you need to transform the index as well as the tensor. Consider it transformation as a tensor here. You need like the gamma mu nu here applying to the vector here to transform the direction of the vector as well. But for the covector, you need to transform covariantly by applying the inverse of the gamma. Okay. For the rank 2 tensor here, you apply gamma here to bring up to bring the old index into the new index here, and then you if it is the covariant rank 2, which it can be considered, I mean, for example here, it can be like the metric tensor. It transform as this one. Okay. And possibly it is useful to consider the infinitesimal transformation. For example, the Lorentz transformation can be written as the identity, which is the Kronecker delta here plus something. But because of the property of the Lorentz transformation, it turned out that this omega here, omega mu nu here, is anti-symmetric here in lower index. Here. And what we transform, infinitesimally transform here, is the new coordinate is the old coordinate plus some omega plus some contraction here, which is omega x here. And by this we can find the change in field. And by the change in field, we need to consider it at the same space-time point here. Remember here, it is the change of the field at the point x here is the new field at the point x minus of the old field or the untransformed field at the point x here equal to this guy. Okay. And we can do the same to the remaining field. For example, the vector field, the covector field, the rank 2 tensor field, blah, blah, blah. And you can apply it to translation as well, which is easier, and the form is shown in the slide here. And you may be curious about the the tense, sorry, you may curious about the spinor field. The spinor field uses different representation of Lorentz transformation, which I'm not going to talk here. Okay. Okay. Previously, we discussed the actual space-time transformation, which is the coordinate transformation. But there is another kind of transformation which act directly to the field itself, which is called the internal transformation, or I say it as internal symmetry. Here, it is the internal transformation that is said the internal transformation because it doesn't act directly on the space-time, meaning that the space-time is the same thing. I mean, X is still X. But it acts directly on the field. It acts directly on the field. For example, if you consider this kind of multiplex field here, okay, let's say it have component 1 to n here, and then you consider the transformation that this transformation basically mix. The result in this transformation is that it mix the components of the field by applying the matrix U. Okay, and the change in phi star is minus I alpha phi star here, and it is not hard to find that with this change, it doesn't change your Lagrangian, such that this is considered the symmetry of the system. But we can learn that because this is the symmetry of the system by the Noether theorem, there exists what is called the conserved current J that satisfying the continuity equation. Okay, and by the conserved current you can construct the conserved charge as well. This is the example of the SUN. Okay, this is what I told you earlier. If you have the multiplet phi here and then you change it into U phi, where U is the finite transformation probably in SUN here, where for the SUN, the generator satisfies the commutation relation here, where the F here is called the structure constant. Then you can find that infinitesimally that the chain in field is this form, and then you can prove that, I mean, if if this transformation is the symmetry of the theory, from the Noether theorem, it said that you can construct the conserved charge corresponding to the generator, each generator. So there is basically n square minus 1 conserved charge. Sorry, there is n square minus 1 conserved current with correspondingly to n square minus 1 Noether charges. Okay, let's talk about Noether theorem. Let's talk about Noether theorem. The Noether theorem says that if your theory has symmetry that exists the conserved current. Okay, let's see that if I consider the chain in the field here, and then obviously that the Lagrangian changes by this amount. Okay, the first one here is the equation of motion, so it would be 0. What is left is here the total derivative term, right? But you know that, as I shown you earlier, that if this transformation is actually the symmetry, it means that the chain in Lagrangian need to be equal to some total derivative of some object here. Let's say it is k mu here, such that I can introduce a conserved current, which is this guy minus this guy here, and it satisfies the continuity equation here. So it means that for every symmetry, global symmetry, that exists the conserved current satisfying the continuity equation. Okay, and from the conserved current, we can construct the conserved charge. Basically, because the conserved current is J mu, right? We can construct the conserved charge Q as the spatial integration or 3D integration of the J0. Why is that? Because if I apply the time derivative to the Q, if I apply the time derivative to it, you can use this continuity equation to rewrite the dq by dt as some integral around the boundary, and you can consider it as the flux that go out of this enclosed boundary. If there is no flux out, so you can say that upon the suitable boundary condition, you can say that dq by dt is 0, so that the charge is conserved. Okay, so this is an example of the Noether theorem. So if Noether theorem say that you have symmetry, you have the conservation laws, such that, for example, you have time translation. If your system has time translation symmetry, you have this kind of current here, and then you conserve the conserved charge is the energy. And if you theory have spatial translation, your conserved quantity is momentum, and the Lorentz transformation, you conserve, actually the conserved current is angular momentum is part of it, but there is the basically the boosted part of the charge as well. It contains 6 charges for the Lorentz transformation. And for the U1, it is like the internal charge. And SUN is also the internal charge as well. If it is SU3, you can think of it as the color charge. And for a physics example, For the episode example, I'm going to consider the Klein-Gordon theory, with the translation symmetry. Okay. For the translation symmetry that I send x into x plus a, where a is some constant, it is globally defined, which is a constant here, such that by changing this coordinate transformation here, the field changed by this amount, and then the field changed by this amount, that is give you that the Lagrangian changed by this amount too, such that you can put it into together and compute the conserved current J as here. Because A is, let's say A is arbitrary constant, you can pull up A out of everything. You can factor out A, vector A here. Whatever inside here, we can say that whatever inside here, we can define it as energy momentum tensor here. Okay. Yeah, as I said that I would define whatever inside this bracket here as another object, which is called the energy momentum tensor, but I call it canonical energy momentum tensor, where T mu nu here defined by this. Therefore, if I put in the form of Lagrangian here, I would get my energy momentum tensor as in this form here. And my energy momentum tensor satisfy the continuity equation as well. Okay. And by the energy momentum tensor, if I set mu to 0, such that I can end up with basically define the conserved charges which is 4 charges, right? With respect to mu is 0 is related to the conserved energy, and when mu is in the spatial direction is correspond to the conserved momentum. Okay. And just to be noted that for the scalar field, the energy momentum tensor is in this form, and it turned out that it is symmetric. It is symmetric. T mu nu equal to T mu nu, right? But it's not generally true. It's not generally true. This is a very special case for the scalar field. For example, if you include the Dirac field or the vector field, this energy momentum tensor or the canonical energy momentum tensor, it generally not necessary to be symmetric. But you may learn previously that if you're working with the gravity, you expect that your energy momentum tensor to be symmetric, right? Because it is basically the energy momentum tensor proportional to the change of the action of the matter with respect to the change of the G mu nu or the metric tensor. Because the metric tensor is symmetric, you expect that for the GR, the source of the gravity or the energy momentum tensor to be symmetric, right? But from the symmetry point of view, in general, it's not symmetric. It's not symmetric. We can make it symmetric by using what is called the Belinfante-Rosenfeld improvement. Okay? So let me call it BR, Belinfante-Rosenfeld energy momentum tensor here. You can symmetrize the energy, you can symmetrize the canonical energy momentum tensor by adding something here. By adding some object here, which is the B object here, which is anti-symmetric in the first two indices, such that if you switch lambda and mu, you get the minus sign here. This property guarantee that if you do the double derivative with respect to the first two index, it would be 0, such that it would guarantee that your new energy momentum tensor would satisfy the continuity equation. By doing that, you can match this improvement of the energy momentum tensor to the Hilbert stress energy tensor defined by this that you already seen. Because this, as I said earlier, that this is the source of your gravity, right? So it's expected to be symmetric. Okay, next, we talk about symmetry. Usually it is the global symmetry, but let's move from global to local symmetry, such that, for example, for the global symmetry, you may consider the phase shift here, where the alpha here is constant. It means that for every point in the space-time, you flip or you rotate the field you rotate the field at every point in space-time by the same amount. But what if the symmetry is local, such that you turn the global parameter into the local one that depending on the point in space-time? It turns out that if you do that, it turns out that the derivative of the field itself, if you consider the change, it turns out is not transformed covalently. It's not transformed covalently. This is the problem. If you expect that your theory have local symmetry, you need to find a way that your derivative of the field to transform covalently as well. It means that the ordinary derivative is not enough. You need to change this thing into what is called the covariant derivative. Okay, so by changing normal derivative into the covariant derivative, you need to introduce what is called the connection. And by the connection here, for this particular example here, I use the A, which is basically the gauge field as the connection. And it turned out that if I introduce this gauge field here with together with okay, the pointer doesn't work. Okay, it turned normal. Together with the transformation of the gauge field written in here, it turned out that you can make you can make the covariant derivative to transform covalently, such that the d mu phi transform into like the phase applying to the d mu phi. Okay, and if you familiar with the, let's say the EM or something here, this is the gauge transformation of the, this is the gauge transformation of the of the gauge field, or in EM it is a gauge potential, right? Gauge potential and gauge and a potential vector. Okay, meaning that if you would like your theory to be locally gauge invariant, you may need to change the normal derivative into the covariant derivative, but in exchange you introduce the gauge field here as a connection. Okay, and it generally the covariant derivative does not commute. When you compute the commutation, d nu here is, you can define what is called the field strength tensor here, f mu nu here. By the f mu nu here, it is a gauge invariant object such that it contains the dynamics. You can create the dynamics of the gauge field by this form here, the f square, f mu nu here. Okay. So this is the way we deal with the trying to construct the gauge, the local gauge invariant theory. Next, let's talk about another kind of Noether theorem. We learned that the first kind of Noether theorem dealing with the global transformation, right? If there is a global symmetry, there exists the conservation laws. But then if the symmetry is local, what for example here, if this is the parameter epsilon, if the epsilon depending on the space-time x, your field can be written as the change, as the epsilon or the derivative of epsilon or the second derivative of epsilon, blah, blah, blah. Okay, if you can written in here and then you vary the action here, and then if you vary the action and then you do some algebra trying to rewrite everything in terms of the epsilon, because epsilon here is our change, is our change. Then you end up with this kind of equation here, where E here is the Euler-Lagrange term here, and the R here is basically the coefficient of the expansion of the expansion. So we end up with what is called the Noether identity of the Noether identity. You will see why it's called identity, because it is obviously true. For example, For example, if you are dealing with the Maxwell equation, Maxwell Lagrangian here with the local transformation in gauge field here, d mu alpha x here. So because of the chain in A is here, basically the mu alpha here. So the chain in action here is basically this, right? And then by this, you can do a part, sorry, you can do the by part, integration by part, and ignore the boundary term, you get this guy here. And because the action is, and because the delta S is 0, so you expect that this guy is 0. The derivative of this guy is 0, right? But for the action of the Maxwell theory, it is basically here. The mu f nu mu here, such that you end up with this identity, which obviously is true because f mu nu is anti-symmetric, right? If you do the double derivative, it is 0. But it tells you something that the energy, oh sorry, the equation of motion, the equation of motion, this is the equation of motion, right? Equal to 0. It is the equation of motion. You expect to have 4 equations of motion, but in general, these equations of motion are not independently. It's not independent to each other. It's related by this guy here, meaning that your gauge field A mu nu is not totally independent to each other. Therefore, it contains what is called the gauge redundancy, right? The concept is that the gauge transformation is basically related. If it is the symmetry of the theory is related, even though the configuration are distinct to each other, but it related to the same physics, right? That means it is the redundancy of the description of the field. So, therefore, we need to get rid of the unphysical or the unobservable degree of freedom by applying the gauge choice or the gauge fixing. For example, here, if you are going to, normally you have a mu which have 4 components here, but it turned out that you can fix the gauge. You can fix the gauge by 2 degrees of freedom to get 2 physical degree of freedom. And from the gravity point of view, E mu nu have 10 degrees of freedom, right? Because it rank 2 tensor, symmetric rank 2 tensor. You can get rid of 8 unphysical degree of freedom to get 2 degrees of freedom. And I believe we will discuss this later in Ajahn Pichet this afternoon. So I would put the, if you would like to ask this, just ask Ajahn Pichet in the state. Okay. 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 Let's move from gauge theory to gravity. So this I will give you some idea or show you some similarity between gauge theory and gravity. So in gauge theory, you have the field A as the connection because you introduce the connection A to the way that you make the theory locally gauge invariant, right? So in gravity, you have connection as well, which is the Christopher symbol. is a Christopher symbol here. And then you have in gauge theory, you have the covariant derivative, and in gravity you have the covariant derivative as well. Yeah. If I mean it's not the same kind, it's a different kind, but it transform covalently. In gravity, it's transformed covalently mean it transform tensorally. It transform in tensor way. Okay. In gauge theory, you have basically the field strength tensor, which can but in gravity you have the Riemann curvature tensor. You can see that in gauge theory you define the field strength by the commutation between the mu and the nu here. But in gravity you have the same kind. You have the same kind of the Riemann curvature tensor by commutation of the gravitational covariant derivative. So the idea is that in gauge theory, you're dealing with, you try to make the theory locally gauge invariant. So in gravity, if you would like to do the analog to the gauge theory, so you consider in field theory, you consider, for example, U1 into local U1, and you introduce the gauge field, and then roughly speaking or hand-wavingly speaking, if in general relativity you did the theory that have the coordinate transformation, and then you consider it as the local coordinate transformation, and then you end up with the metric tensor as the dynamical variables. Okay, by the local coordinate transformation, I mean this. You change or you transform the coordinate x into x prime that depends on the local point in the untransformed coordinate x here, and then you vector field transform at this. Then by this, you can define the covariant derivative here, where this symbol here is the connection here, such that this would transform covalently under this tensor transformation. Okay, and then if you apply more detail, I mean more conditions such as the metric compatibility and torsion-free gravity, and then you end up that this is the Levi-Civita symbol, I believe, like this. And then similar to the gauge field where you introduce the field strength, in GR you introduce what is called the Riemann, not Riemann, it is Riemann, the Riemann curvature tensor. And if you by this, okay, and from the Riemann curvature tensor, if you contract some indices, you get the Ricci tensor and then the Ricci scalar. And this is the ingredient. Okay, I think we are on time. I have like 2 slides left. I have ingredient to construct the action, which is the Einstein-Hilbert action here, which is I have the mu nu, which is the dynamical variable, and the R, which is scalar. I mean, the square root here is to make the measure or the for x square root basically transform invariantly. So this is the gravitational part of the action. If you if you do the principle of lead action, you would end up with the Einstein field equation without matter source. But if you would like to include the matter, you could include the matter section of the action here. For example, you can include the scalar matter. Here can be whatever. Okay. So in general, the general relativity would have this kind of term here. And then if you do the variation, you end up with the Einstein field equation with the source term as the energy momentum tensor from the matter field. You can this is the general relativity action, but in general, you can add more. You can add more, but we need to add some term that generally make the transformation invariant term. For example, we can add r square, r mu nu, whatever. That already contraction, or maybe this you may call it like the FR gravity. And this is the way you can not define. This is the way you can modify your gravity. You can modify the gravity in this R section that is what the school is all about, the modified gravity. But on another half, you can put these R the same, but what you can do, you can add matter. You can add matter, add energy, such as whatever it is, whatever the matter is. It could be some dark matter. It could be like some stellar neutrino. Could be cold dark matter, whatever. So that is another way to modify. Let's say that if you modify the R, that means you change the Einstein field theory. But if you add matter here, you would leave the R alone, and here you try to make the. By the way, this is all the way that you can that you can make modified gravity to make the theory to match with the observation that we have today. Okay, that would be all for my review. You guys have questions?
Questions. Head.
Okay. If not, it's okay. It's okay. Totally fine. You can ask whoever. Not me.
Head. Okay. If you don't have questions, please thank speaker again. And this is time to lunch now. It's outside, and then you can walk to the canteen. It's not around here. You can walk. You need to walk a bit. There are other group that have lunch box, but around here is not us. It's not for us. So that you have to walk a bit to the canteen. I think they have staff to take you to there. And okay, the afternoon session we will begin at. Who remember? 1 o'clock, I suppose. 1 or 1:30. 1, okay. So now let's move to have lunch.